Now that we've played around with sonifying sound sources in binaural, we will move into working with multi-channel arrays. Speaker placements and arrangements have been evolving ever since the advent of amplified sound. We've gone from mono to stereo to surround. We're continuing to add more and more channels. We're continuing to add height speakers. And now we have high-density loudspeaker arrays like the Cube at Virginia Tech. You can see in this image that there are 64 channels, all at ear level, that create a high-resolution image on the horizontal plane. There are another 76 speakers arranged as height speakers in this array. At this point in time, there are many different arrangements of speakers and ways we can set up speaker arrays. This is dependent on what your goals are for your output. For this demonstration, we will be using a simple quad setup. All right, we're going to talk about higher order ambisonics. Higher order ambisonics is a very popular technique for being able to spatialize sound within three-dimensional speaker arrays. It uses spherical harmonics to create a three-dimensional sound field. You have different orders that create higher and higher resolutions of this spherical sound field. People like to use it because you can rotate the audio field around the viewer, so it's popular in head tracking for VR. It's also flexible and can adapt to different speaker layouts, and it creates a truly immersive feeling. However, the spatial resolution can be fuzzy. You need 64 speakers to do a good 7th order render, and it can be very CPU heavy. So it's definitely a very powerful tool and a very powerful algorithm. However, there are also some other algorithms that aren't as CPU heavy, and you can still get a pretty good effect. Another algorithm that you can use is vector-based amplitude panning. This extends on stereo channel-based panning methodology, and it uses 3 speakers to triangulate sound source instead of 2. There are other versions of these methods, which include distance-based amplitude panning and vector-based intensity panning. They're popular because it uses lower CPU than ambisonics, and you can still decode to different speaker setups, and you're able to create maybe a tighter kind of sound directionality than you are with ambisonics. Wave field synthesis involves producing artificial wavefronts that are synthesized by a number of individually driven speakers. These wavefronts appear to come from a virtual starting point called the notional source or virtual source. Unlike conventional spatialization techniques, the localization of virtual sources in wave field synthesis is not dependent on where their listener is positioned. Wave field synthesis has great spatial resolution. However, you need a lot of speakers to be able to do this well. But it's a very cool technique and a really fun one to play with if you have the tools to do so. Other algorithms that you can play with. I know we've talked about dBAP and BIP a little bit, but there's also K nearest neighbor. That one creates a really cool resolution. It's probably one of my favorite that Spat uses. You can also do just direct to speaker. You don't need to use a spatialization algorithm. You can just use a speaker as long as there's a speaker where you want a sound to be. So we're going to talk a little bit about how to set up your hardware. So the first step is that you need to arrange your speakers. Next, you need to plug in your interface. Following that, you're going to download drivers and configure your interface. Then you will select your interface in Max MSP, and then you will configure your I/O. And finally, you will test your speakers to see if they work. We're going to show a little bit of a demo on how you would do that with this quad system that we have available in the ARTSLab. So the first thing that we will need to do is to set up our speakers. For this arrangement, we decided to go with a quad. So we have 4 speakers that are arranged in a square around us. We want them to all be at a similar height, and we tuned the volume using a decibel meter to be able to tell kind of what the loudness of each speaker was and to try to get them about equal volume. Now, if you have other speakers you want to set up, you can set them up in different arrangements and be able to then measure them later on. So the next step is to plug in your interface. For this particular setup, we are using the Tascam Series 28i. If we go to the back of the Tascam, you can see we have our outputs. For this, I decided to do, because the main monitor is using 1 and 2, I decided to use 3, 4, 5, and 6 for our 4 outputs. I can then route them in our computer to be able to be 1 through 4 on our computer inputs. So to use the Tascam, you need, or really any interface, you need to download their drivers and install them. You can do that by going to their website and finding and Googling the drivers for your device. Once you've downloaded them and installed them, it'll look different depending on the interface you have. But for the Tascam, we have this settings panel that it comes with. Now, we needed to do a little bit of interesting routing to make sure that the settings worked well and that things were getting out of the computer in a good fashion. So again, remember, we plugged into line out 3, 4, 5, and 6. So here, we need to make sure that it's on computer 1, computer 2, computer 3, and computer 4. This will then allow the audio from the computer to go out line, the audio output from computer 1 to go out line out 3, computer 2 to go out line out 4, computer 3 to go out line out 5, and computer 4 to go out line out 6. You also want to think about how your speakers are arranged and which audio input is related to which audio output just when you're making your speaker map later on. So once we have chosen our audio device and made sure that our I/O is configured correctly, I like to create a quick speaker tester to make sure that we're getting sound out of the correct speakers. So to do that, I will create a pink noise. I will also create a live gain. I will connect the pink noise to the live gain, and then I will create a DAC. I will bring the live gain down before connecting it to the DAC to make sure that there are no audio surprises. The next thing I will do is I will create a message with a set, $1 for a variable, and I will connect this to an integer. And then I will use this to be able to control which speaker I am addressing addressing through my DAC. So I'm going to turn the audio on. Hopefully everything sounds good. We're going to set it to 1 and we're going to slowly pull up our fader. You can see that you can hear that we have sound coming out of speaker 1. Now let's try speaker 2. 3, 4. We have sound coming out of all 4 speakers and they are correct in their routing. When using these different algorithms, you will need to create what's called a speaker map. The speaker map tells the decoder where your speakers are located in space so that the decoder can properly spatialize the sound. Values can be recorded using Cartesian, XYZ, or spherical azimuth elevation distance coordinates. I will demonstrate a quick method of using a laser pointer and a protractor to measure azimuth and elevation values for your speaker array. So for this setup, we don't really need to do any measurements. However, if you have more speakers that you want to add, either in your azimuth plane or in your elevation plane, you can use a very simple technique of taking a protractor and taping a laser
pointer to the end of it. You would use the laser pointer
to project the laser pointer dot onto your speaker, and then keeping your protractor in the same spot, you can use this to kind of measure out your azimuth and see where this would be in your azimuth plane. If you want to go a little bit of a step above, this is a cool device that actually kind of tells you the angle here. So you could use this as well as having a laser pointer or something attached to the end. And then you just kind of get your value digitally as you move it around. This one is a little bit better because it can do 360 degrees. This protractor I have doesn't do it, so you would have to move this the other direction while trying to keep it kind of oriented in the same space. And then same for elevation. So you would take this and you would kind of use this, again, keeping it kind of in the same space as you move around, up and down. And same thing with this. You can use this the same way. Another useful tool is one of these guys. If you want to measure, if you want to get really precise with the distance, usually I will map my distance to 1 for the most part. But if you do want to get really precise, this little device also has a laser pointer on the end, and you can use that to go to your speaker. You can click down and it will tell you how far your speaker is away from you. These are also really great little devices if you, and they also have kind of angle orientations too.
All right, we're going to start on our next coding break, and we're going to make everything we've been working with multi-channel. So let's come back over to Max. We have, again, our binaural panner that we've been working with. This time, we are going to look at the Spat 5 pan object. So if we open our help, kind of go in here. So you can see here that there's this giant list of all different panning algorithms that you can work with and use. And so you can kind of explore these with the pan, and then you can decode, use this and then decode it to different speaker arrays. This can be a bit CPU heavy. So I find it's usually best to kind of choose what sort of algorithm that you're wanting to work with and be able to kind of go from there. However, if you want to just like play around with seeing how stuff sounds and how some of these different panning algorithms sound in your space, then feel free to kind of use the pan object and be able to work with that and decode it to your environment. For this particular workshop, we're going to be focusing on ambisonics. And so we're going to use this HOA 3D panning type. But again, I encourage you to go and kind of dig deeper into all these different panning types and just to try them out and see how they sound and what they do. So we're going to come back here to our max patch we've been working on. So we're actually going to delete that one, and we're going to do the spat5.hoa. And we'll do 3D and go. Let's see how that. We'll just do, okay, there we go. So, and then we're also going to add the decoder as well. So one is going to encode our sources into the three-dimensional environment, and the next is going to decode them. So there's a few things that we want to be aware of when we are working with higher order ambisonics. So we can go into our handy help file. And so again, you can see what the attributes are. So you need to kind of define how many inputs you're going to have, what the order of your ambisonics is going to be, and then what dimension it's going to be. So we're going to, for again, the sake of this workshop, let's start with in our encoder at inputs 2. We'll do at order. And we're going to work with 3. I find that 3 is pretty reasonable, especially when you're getting going. Again, some of the higher orders can be pretty heavy on your CPU. So just depending on what kind of computer you're using, will kind of depend on what order you can work with. But if you want to try working with higher orders, feel free. But I think 3 is at least sufficient to kind of get going and at least to be able to experiment and hear where things are at. And then the next thing we're going to add is dimension. And we'll work with, even though we're working with a quad system, I'd still like to keep it in 3D. So we'll do that. So let's look at our decoder now. Okay, so our decoder, now you don't need to define inputs because the inputs are actually being defined in the encoder. And the order is really what's going to be important. So because we're working with order 3 in the encoder, we want to be working with order 3 in the decoder, as well as the dimension. Since we're working with 3D, we also want to work with 3D. And then we're going to define how many outputs we have. Since we're working with a quad system, we're going to have 4. So let's type that in. Okay. So one more thing before we start going with this. As you can see, it's quite a bunch of patch cords that we're going to need to connect. Even with third order, you're still working with 16 channels out. So we're going to introduce and start talking about MC. MC is a handy thing that kind of came about in Max 8 that allows us to be able to put 1,024 channels through just one patch cord, which is amazing and has changed workflows dramatically and makes things so much easier. So the Spat objects allow us to work with MC. All we have to do is say at MC and then say 1. Now you can see how all of those patch cables just got put into 1. Pretty incredible, huh? So we want to do the same thing with our decoder. Now you can see that the patch cord is blue, and when you hover over it, it says 16 channels are being passed between. So again, it's a pretty handy thing, especially when working with multi-channel and so many different speakers. So now we're going to also create our live gain out. And to do that, because we're working with MC, you type mc.live gain. And now if I connect this, and if I turn the audio on, you can see that it automatically creates 4 channels. Pretty cool, huh? And now you can also do an mc.dac object. And so this will output to the first 4 outputs of your DAC. If you need to define those differently, you can type in here. If you wanted it, say, to start at 3, you could do 3, 4, 5, 6. But because we should have set everything up from 1 to 4, we'll just leave it as is. We don't need to define it. All right, so the next thing to do is we can actually just attach our same Spat viewer over to our encoder. And we can start to, and then we will also need to now be able to get these inputs in. So we said that there's 2. So another object that we can use to be able to kind of create put all of these objects into 1 is we can do it mc.pack. And so the mc.pack will allow us to take the output from this source, the output from this source, and we can just attach it directly to here, and that'll be 1, 2. Now, let's just, since we didn't before, add a live gain over here. All right, we're going to talk about one thing I forgot to mention, but is very important. Is remember we created our speaker map. Now we are going to connect that to our decoder. So what we need to do is create a Spat5 viewer. And this time, instead of initting with source, we're going to init with speaker. And we'll say 4 since we have 4 outputs. And now we can connect this to our decoder. And let's double click. You can see that it has created 4 speakers, and they're located in a quad arrangement, a typical quad arrangement. And so this could be fine as long as you make sure that your speakers' outputs are mapped correctly. Now, if you wanted to change that a bit, and then also if you had a more complex multi-channel array and you've done all your measurements with your protractor or one of your fancy little tools, we can create a Spat 5 speaker config. So if you double click on this, it kind of comes up as a 5.1 set up automatically. So that's not really what we want. So let's go into this help. And you can see, I think one of the objects will connect, because if you want to change your output down the road, you can, is this Spat 5 speaker layout. And so it's a pretty fun kind of tool that allows you to move through different speaker layouts that are pre-configured. So here's the stereo one. We can do left, right, center. And you can see they've already kind of loaded all of these different arrangements in here with this bpatcher. So let's just kind of copy paste all of this here, and we will connect it to our speaker config. And now let's choose 4. And if you open this, you can see that we have our 4 speakers. So it's saying left, right, left, center, right, surround. Now, if we wanted to, change this, say we wanted our 1 value to be over here, we can kind of switch this to be, let's see. So let's do, this is going to be, copy this, paste. And we can then change this one to -45. So we just switched our left and our left surround. So you can take your numbers that you have created and you can load them in here, and you can take the amount of speakers you had, and maybe you can start with one of these layouts and then go from there. So do that, and then we'll move on to the next section. Okay, so since we're listening on headphones right now, you're only going to be able to hear the first 2 channels. You won't be able to hear the quad output. But if you do have a quad system set up, or if you have another multi-channel system set up and you want to hear how it's sounding, feel free to plug that in and play it back. So we're going to, play our data source again, and we're going to make sure our audio is turned on. Let's turn this up a bit, and we can. You can see that the audio is playing at all 4 channels now. And so it's moving around in space that way. Okay, we're going to take a quick break, and then we're going to come back and start talking about one more sonification technique that we can use with the MC objects. All right, so we're going to kind of wrap up this workshop by creating one more sound. We're going to use the MC objects and dive a bit deeper into those. And then we're also going to explore how to map that to a multi-channel output. So to get going, we're actually going to create a new subpatcher. And I'm just going to call it Triangles Fun. So with MC, the MC wrapper is kind of a wrapper that goes around pretty much all MSP objects. So any object in the MSP library pretty much has an MC version of it. And all you have to do is type in MC, and then we're going to do triangle because we're going to work with some triangle waves. And so we've created a triangle wave with an MC wrapper. Now, if we add to this triangle wave chans 16, what we've done is we've created an object that has 16 triangle waves within one object. So that's pretty exciting. So now that we have these 16 triangle waves in this one object, how do we actually address them? We're going to start with the target object. So if we, go in here and we click on the help, you can see the MC target object simplifies the creating of set value messages used to target specific instances. So this is how, we can kind of target some different, create different values. You'll notice over here too, that you also need to target the voice number. So hold on to that and we're going to come back to that real quick. So if you go over to this polyphony tab here, you can see an example of how the MC.target object is kind of being used. So let's turn this on and kind of listen to it a bit. Yeah, that sounds pretty cool, right? So what's happening is you have a metro that's kind of triggering this voice allocator, MC voice allocator. This is kind of changing the voice for the target. It's also kind of going into this patch that's creating sort of some random messages that are then creating these different values that are then targeting the cycle object that has 30 channels. So let's kind of try to recreate this a little bit. So we're going to patch the MC target over here to this MC triangle that we're using. We're not going to do the tune generator because that's actually going to be our receive, and let's do our velocity value that we've been using. And that will be our data at that point that we've been using here. And then let's go with the MC dot voice allocator. We're going to do 16, and we will hear this here. And then we're going to have so again, you see kind of this metro object that's creating this rhythm. So let's actually create a receive. We're going to connect that here. And let's go back to our data patch here, and let's add a receive to our counter, or a send to our counter. So call it change. So anytime our counter outputs a bang, it's going to send to this change, and that's going to be what's triggering our voice allocator. Now that we're here in our voice allocator, we can close this out. Now let's also add an MC.live or MC.meter. So this will allow us to see, kind of what's happening and what's going on. So let's come back here to our target, and we can kind of look at this a little bit in comparison. So, all right, let's try turning this on. Let's turn this down so we're not listening to that all the time. And so you can see, okay, we have some triangle waves that are playing out of this object. Great. But they're not kind of going in this pattern similar to this one. Why is that? So that's because this is using this line object. So let's add that in. And we'll do at chans 16. We also will have the MC.target. So we also want to send the voice allocator to that actually. Sorry, we did the wrong. We'll send this output is the voice number. So this is messages out. So we'll do that. It's the right one. We will also send that to the target. And instead of, this kind of envelope function box that we're using here, we're just going to do kind of a direct message of 1,000. We could add this envelope if you want. to get fancy. And then this is also going to receive the change value. Now let's add a MC signal multiplier. We will connect these two. Now we kind of want to, hear what this sounds like, right? So we can also do this MC.mixdown, similar to what they're using here. This just takes all the channels that are available and mixes them down into one, into however many channels you would like to mix them down into. Let's also do a new live MC.live.gain. And again, if you hover over, you can see how many channels are coming out. And now we'll do an MC dot DAC. Okay, let's turn that down and we'll turn our audio on. So you can hear that the triangle waves are changing and kind of creating this pretty interesting type of tone. We can still, actually receive, do our, change our duty cycle too. So we have let's do that. So now we have all of these triangle waves, but they're just kind of creating this interesting buildup and creating kind of a complex tone. Now, what happens if we actually take that tone that we've created and put it into multi-channel? So let's create an outlet or a new outlet. And we can kind of send this signal out here. And now let's connect this. We're going to connect this to our binaural object. So let's actually turn our binaural object into an MC1, MC with the MC wrapper. And let's change our sources to 16. We'll deconnect these for right now. And we're going to change all of this so that it's an MC as well. An MC wrapper. Cool. Let's turn the audio off for that. Awesome. So now we can connect our triangle wave here. The next thing that we're going to have to do is we're going to have to change our spat viewer and to 16 channels. But let's also kind of unconnect that so that that's not controlling those sources. So you can see it kind of creates an interesting little kind of circle pattern sort of right off the bat. Now, let's see how this is sounding. Cool, huh? And again, you can play that out of your quad system. And if you want to start playing, with kind of controlling some of the different source positions. There's some fun things you can do there as well. One last object I'm going to talk about quickly, but not dive too deeply into it, is actually this Spat 5 grids object. And so this object kind of allows you to create some really interesting patterns in your viewer. So if we open this up, you can see we've kind of got this interesting patterns that are being grids that are kind of being created, and you can kind of go through and you can change those and play with them. You can also do these cool transformations on these grids. So I encourage you to, maybe start playing with creating some of these different waveforms and assigning them to some of these different sources. And then you could actually use some of the data sets to control the yaw, the pitch, the roll. There's also the scaling value, and just start seeing how that sounds and what kind of fun things you can do that way. So I think this is an interesting way to start to take some of these concepts that we've been working with, and apply them into multi-channel, and then start to really go crazy with it. So I hope this kind of gets you going, and you can start to really explore all different types of ways to sonify data and be able to kind of create interesting sonifications that are thought out and have some interesting sonic properties. So good luck.
This concludes this module. For further engagement, you can create your own decoder to output to your own multi-channel speaker array, and you can play with different decoding algorithms to see how they sound within your multi-channel array. Our last module is going to talk a little bit about open sound control. So open sound control, or OSC, is a protocol used to send messages between computers, synthesizers, audio software, and other multimedia devices over a network. It was developed as a more flexible and modern alternative to MIDI. OSC is integrated into many softwares and apps and can be easily programmed. In my Orbits piece, I used OSC to map the gloves that I use to control different values parameters in my instrument. You can also map values from Unity or Unreal to have the audio relate to visual events within virtual reality. I will be using TouchOSC, which is a cheap app that you can download on your phone or iPad to demo how to set up and control different parameters within Max MSP.
Okay, so as a little bit of an extra credit assignment, we're going to kind of explore how to connect OSC to this patch. So one of my favorite things to control over OSC is the tempo of the patch. So that actually how quickly you're moving through the data. So I'll just quickly kind of show you what I have done to be able to do that. So I open the global transport, and we go into the edit mode or kind of take it out of presentation mode. And then you can double click on this view here. And then this will actually, if you click on this tab here, it'll actually kind of open up the full thing. So then you can kind of go in here. If you don't want to mess up this kind of global transport as it is, you could copy and paste this and create your own, or you can just add a simple send, receive kind of tempo value here, and kind of put that in here. So now if we go over somewhere else in the to kind of another part of the patch, and we say send tempo and create an integer value, connect it. You can watch that that's actually being controlled. So, and then you can kind of go back in here, and you could save that, as your own kind of saved global transport.
So if you would like to follow along with this section, we will be using TouchOSC, downloaded from the App Store. It's a cheap app, and I highly encourage getting it, as it is very useful and can be a lot of fun to play with. So if we open up TouchOSC, initially we kind of come to this page. There are a lot of, this is kind of the default layout, and you have a couple different layouts that you can kind of choose from. If we kind of come through here, and each layout, has different faders or buttons and toggles, and these all send OSC messages. So to be able to start playing with these layouts, we will need to make sure that our phone is connected to the same Wi-Fi as our computer, and then we will need to go in to our settings panel here, and we go to our connections, and we need to look at this host IP address. And we will need to match that to our computer IP address. You also want to look at the port, the outgoing port, and the incoming port. Any message that you send or that is receiving in Max MSP needs to be able to match this incoming port. So we will go into Max MSP for a bit and build an incoming OSC port. So in Max MSP, the first thing to be able to capture OSC is we need to create a new UDP receive object. And we will take the port, which was 7500. That was coming in, outgoing from our OSC device, and attach that. Next, we can create a message box to be able to see if we are connected. So let's go back to our phone. And we can now move the fader. Currently, we are not getting any input in Max MSP. So we said 7500, it's actually 7050. So we need to change our incoming port to 7050. Now, if we come back here to our thing, we should get an incoming value. Yay. Okay. So now coming back into Max MSP, you see that we have this /1/fader. What we will want to do is create a new OSC route object. And then we can route out the \1/fader. So now we can take that message. We go back to our phone. And we do that. Oh. It's fader number 5. So we see the 5 here. So we need to add that. So let's try this again. All right. So now we have a value going in to Max MSP that is scaled from 0 to 1. So the next thing that we will have to do is figure out what we are mapping it to. So for the purposes of this, I'm going to map it to our, this kind of project, I'm going to map it to our tempo. So the next thing that I will do is scale the value between 0, 1, to, I'd say 10 to about 300. I feel like that's a good range. Now, I can connect this and we'll get the message value. Let's try this again. All right. So now the value is scaled between 0 and 1, or between 10 and 300. And the next thing that we're going to do is send to our tempo that we've already created a receive for. So now, if we look at our tempo over here, let's watch as it changes and is now being controlled with our fader. You can go and you can play with all the different faders and different kind of buttons within this. You also have different layouts that you can explore. You're also able to make your own layouts on your computer and upload them to your app. And you can use this on your phone, you can use it on an iPad, and be able to use it as a control interface for any kinds of programs that you are developing. So for further engagement on this module, add OSC. Using TouchOSC or another device or software, map control values to different components in your patch and bring it to life. So now we're at the end of this workshop, and we will show a final demo of some of the stuff we have been working on. All right, so we've been working on building out some of these sounds and connecting them to some different encoders and decoders and connecting them to multi-channel. And now we're going to kind of take a second and listen to how some of this could maybe sound within a quad system. So we have our data set we've been working with over here, loaded into this text box here. And when we kind of trigger our metronome, it's going to start moving through those text boxes. And you can kind of see that the data is changing as the metronome is going. Right now our tempo is set to 10, so it's pretty slow. So we can maybe bump it up to 30 and move through some of the data points a little bit quicker. And this is, starting to control kind of the movement of some of our sound sources. And then as well as some of, you can see, kind of some of the changes that are happening as we've mapped them, to these different data points. So let's hear how this sounds. So our first sound, we'll just play, is our basic sine signal that's being controlled, having the pitch controlled by one of our data points, and it's being moved around also by one of our data points. So very basic, nothing too exciting, but still kind of gives you an idea of how to start with this type of stuff. Now, this is our triangle tone that right over here that we're working with. This is the one This is the tone where we are using data to kind of help alter the tonality of the triangle tone at the same time as the pitch of the triangle tone, at the same time as the position of the triangle tone. So let's listen to that one more time. You can hear that we're starting to get a lot more texture. There's a lot more kind of intrigue and timbre to that sound. Of course, you can play with some of the data, which data points are controlling which parts of that sound, and see kind of what tones you like and where you can get with that. And then this is our third sound that we've been working on. And so this is the sound where we're using triangles and we're changing triangle waves, and we're changing them kind of and positioning them around in a kind of circular space. So each of them has a point that's related to one of these points in this circle. And those points, those sound sources are being kind of distributed as each triangle tone plays, going up in being controlled by the pitch is being controlled by different values as you're moving through the data set. And then that data set is creating these triangle tones that are being positioned around in a circle within the quad system, spatialized into that space, and creating kind of a more beating, sort of interesting frequency relationship type of tone, where you can really start to hear the relationship between each data point within kind of a 16 data point set. So let's listen to that one more time. really love this technique to create just these really beautiful immersive textures. You can also use this technique with just a direct-to-speaker approach. So if you have more speakers than a quad, you could take each triangle wave and just assign it to a different speaker and have them play and kind of move through the different speakers that you have available to you, and creating, again, these large textured soundscapes with these really interesting relationships between different data points and that create different sounds and frequencies to be able to hear that relationship. The last thing that we were doing, and I think you can kind of maybe hear it pretty well with this sine tone as well as our triangle tone. Maybe we'll play both tones. Maybe we'll play all three tones at the same time. See what happens. But for this, we're gonna include our OSC now. So we're incorporating our OSC to be able to control the tempo value, which is how quickly we are moving through the data set. I find that to also be a really interesting technique that allows us to explore data in different temporal scales and being able to relate to it in a different way on that front. Well, I hope you enjoyed being able to experiment with data and sound and finding different ways to map it, and had a good time in this workshop.
We hope this workshop has been beneficial for your practice and research. ARTSLab is a place where artists and researchers across disciplines can collaborate and explore new ideas. ARTSLab and CITH are here to support the community with education and accessibility to emerging technologies. If you have questions or would like to get involved with ARTSLab, subscribe to our email list or follow us on Instagram to stay up to date with our events, workshops, and exhibitions.